Hello everyone. Today we will be going to study this new topic of solid state physics. This is lattice vibrations. So, a lattice can be regarded as a regular arrangement of atoms which are joined together by elastic springs. So, in 2D, you can consider a system of spring mass system. Spring mass system. This spring mass system is representing the regular arrangement of atoms, where each dot is representing the atom, and this spring is representing the interaction between any two of the atoms. Now, if you see here, all these atoms are connected together. So basically, the motion of any single atom is coupled with the all other neighboring atoms. So this becomes a coupled motion. Now, for the lattice vibration, there are two choices. First choice is this lattice. It can freely vibrate in its normal mode, or there can be some forced vibrations. So these free vibrations, this could be because of its internal energy, due to internal energy, while the force vibrations can be all two origins. First one is because of some mechanical energy or some mechanical force, or it can be because of some electromagnetic force. So this first type of mechanical force, for example, it could be because of sound, while in this case example, this could be because of course, this visible light. It is not necessary that it should be visible light. It could be because of IR or UV and other part of spectrum, EM spectrum. Now this vibration of this first type, this gives informations related to thermal properties of system, or thermal properties of lattice. So this, for example, this can give me information about the specific heat or thermal conductivity of lattice. While the second type of forced vibrations, they can give me two type of information. For mechanical force, such as generated by sounds, they can give me some acoustical properties of the lattice, acoustical, while this EM force, this can give us information about the optical properties. So in this course we will be studying this thermal properties related to lattice. We will not go into deep into acoustical and optical properties. Now, to begin with, let us consider the vibration of 1D monoatomic lattice. So you can consider a 1D monoatomic lattice as a spring mass system, 1D spring mass system, where each mass is connected with a spring with the spring constant beta, and these atoms are equally spaced with a lattice spacing of A. So that I can assign the position of each atom with its displacement. Let's say this is xn. So the next displacement will be xn plus 1, and this displacement will be xn minus 1. So where this xn is representing nth atom and the displacement and the lattice spacing. So this is the position of nth atom at equilibrium. So consider this is a state of equilibrium where the atoms are situated at xn positions. Now I am trying to disturb this equilibrium by when these atoms they are vibrating about their mean position. So all these xn's, so these are representing the mean position. So let's say this xn is slightly disturbed from this position to this, and all these atoms are displaced. This earlier was my state of equilibrium. Now it becomes state of displacement. And consider the net displacement is un. So un is the net displacement of this nth atom from its mean position. So similarly, this n plus 1 atom will have a net displacement of un plus 1, and then similarly for this un minus 1. Now if you see here, this forms a discrete system. Why discrete? Because the atoms are not continuously placed, so there is some gap in between any two atoms. So this forms a non-homogeneous medium. So this forms a non-homogeneous medium which is distinguished from any homogeneous medium where the line of atoms is continuous without any breaks in between. So but here there is some break in between any two atoms, right? So this forms a non-homogeneous medium. Now in the state of this vibratory motion along x-axis, so the atoms will execute a periodic motion, okay, about their equilibrium positions, and they become a source of elastic waves which propagates through this medium. So in the state of this vibratory motion along x-axis, these atoms execute periodic motion about their mean positions, and they become the source of elastic waves which propagate through the medium. Now let us consider that these springs are ideal so that the force between any two atoms will be linear. So this means that the force required to produce an atom displacement is proportional to the displacement itself. This means that this force is beta times the displacement u, and I am assuming that the force acting on this particular un atom is only because of its two neighbors, that is un plus 1 and un minus 1. So therefore I can calculate net force acting on nth atom. So in nth atom, the force could be because of either this spring and this spring. The force could be because of this first spring and this second spring. So the force will be because of these two springs. So in this first spring, this force will become beta times the net displacement, and the net displacement will be this displacement minus this displacement. So that is un plus 1 minus un, and then minus beta times this displacement un minus 1 and then un plus 1. So that will be un minus 1. So let's try to simplify this. So this will become beta, and then there are two negative of uns and then positive of un plus 1 and un minus 1. This becomes our equation of motion for the nth particle or nth atom. Now use Newton's second law to write this force in terms of displacement. So that this becomes displacement of nth atom. So beta un plus 1 plus un minus 1 minus 2un, where this particular thing, that is d square un of dt square, it is representing the acceleration of nth atom. So therefore in this situation we are expecting a periodic motion. So therefore let's assume that the solution of this above differential equation be some periodic function which is defined as un, some amplitude u naught, and then exponential iota omega t minus k and a. So where this na is nothing but xn. So this is a plane wave solution which represent a periodic motion. Here this kn is representing the wave vector. Wave vector equal to 2 pi by lambda. And omega is representing the angular frequency of vibration. Now similarly we can write these periodic solutions for n plus 1th displacement. And n minus 1th displacement. Now let's try to substitute this equation 2, 3, 4 in this equation of motion. Now let's try to substitute these displacements in the equation of motion, and before that let's try to find this del square of any un with respect to time Before that, let's try to find the double time derivative of displacement. So that will be just iota omega square un, and this un plus 1 you can write in terms of un as e raised to power iota minus ka and then un. So you can take out this ka factor out of this exponential, and similarly un minus 1 you can write e raised to power iota ka un. So let's try to put all these results in the equation of motion. So what we will get, mass times iota omega square un will be beta, un plus 1 is un and then e raised to power minus iota k, plus un minus 1 is un e raised to power plus iota k, and then minus of 2 un. So let's cancel un from both sides. So what we left with is minus m omega square is equal to beta, and we can write this as 2 times cos k and then minus 2, or we can write omega square as beta divided by m, 2 beta divided by m, and then 1 minus cos k. Now as you know that cos 2 theta is equal to 1 minus 2 sine square theta, so therefore cos ka you can write as 1 minus 2 sine square ka divided by 2. So therefore omega will be plus minus under root 2 beta divided by m, and then 1 minus plus 2 sine square ka divided by 2, and then whole raised to power half. So this 1 and 1 cancels out, so what you will get is omega equal to plus minus under root of 4 beta divided by m, and then sine ka by 2. So this is the dispersion relation for a 1D linear monoatomic chain. Now since the frequency omega should be always positive irrespective of this value of k, that is wave vector, so we can write this dispersion relation as omega equal to under root 4 beta by m, then mod sine ka by 2. This becomes our dispersion relation for 1D monoatomic lattice. Now let us define longitudinal stiffness. So this longitudinal stiffness is denoted by C, and this is equal to the spring constant times the lattice spacing. So this is representing the longitudinal stiffness. Now we can also represent the mass per unit length as mass density, that is rho, that will be equal to mass divided by A. Now these two quantities are specific for a lattice. So this means that we can modify our dispersion relation, which is very specific to any given lattice. So what we can do, we can write omega equal to under root of 4 times, in place of beta I can replace C divided by A, and in place of mass I can write rho times A, and this is mod of sine of Ka by 2. And simplify this, then you will get 2 divided by A, then under root of C divided by rho mod sine Ka by 2. Now if you notice, this under root C by rho, this has dimension of velocity. This has dimensions of velocity, and that's why we call this as velocity of sound in the lattice. So therefore Vs equal to C divided by rho, where C is the longitudinal stiffness and rho is the mass per unit length. So therefore dispersion relation will be omega equal to 2 by A Vs then mod sine Ka by 2. So let's end this topic here, and in the next video we will plot this dispersion relation, and we will see what are the limiting cases for this dispersion relation. Thank you so much for watching this video.